Okay, welcome to week 3, lecture 2. We're going to take more of a look at pandas. In the first lecture, we looked at series, and in this lecture, we're going to look at another very important data type that pandas provides, which is the data frame. I'm going to punt on these two little quiz slides. Let's just move to the fourth slide here. So a data frame in pandas is analogous to a table in a relational database or a typical spreadsheet in Excel. That is, a data frame is a structure that has named columns which describe various attributes, and also rows, which are like observations of people or days or what have you. So we might have a data frame consisting of maybe the columns would represent counties in Pennsylvania, and maybe the rows would represent days in Pennsylvania during a year, and the individual cell values would be for perhaps the number of flu outbreaks registered in each county on each day. Both the columns, the columns definitely should be named so that it's clear what each attribute is. Rows can simply be indexed by number, observation 0, observation 1, observation 2, or whatever. Or they can be named. One way of naming a row might be to use today's or the date on which the observation took place. Now, the row names themselves are not considered to be part of the data, and so the row names themselves would not be used in computing things like averages, standard deviations, or what have you of the actual data in the data frame. Here is an example in which we're going to create a data frame. Now, in order to do this, I had better remember to import pandas as PD, and I should also just automatically import NumPy as NP, because it's likely that I'll also be using NumPy in this. Okay, so on Tuesday, lecture 1, we created a series. Let me do that. S1 is pd.series. We created a series from a dictionary. For example, we could have a key A with a value of 1234, and a key B with a value of 43, and a key C with a value of 567, let's say. And when we did this, the keys for the dictionary were used as the labels in the series. And these values, 1234, 43, 567, become the values. What did I do? Oh, rats. I used a comma instead of a colon, so let me fix that. All right. Let me fix that. So this guy ought to be a colon instead of a comma. And here we go. So now here's my series with values 1234, 43, 567, and labels ABC. Now, the primary difference between a series and a data frame is that a data frame is two-dimensional. It has multiple columns. And each column has a name. So here is an example of a data frame also built using a dictionary. But in this case, here's my dictionary. Okay. And in this case, notice that each key is associated with a list of values. All right, so for name here, I have 3 values, Smith, Jones, and Zhang. My next attribute is age, and these attributes, by the way, these keys here are going to become the column names in my data frame. So one column is name, another column is age, 42, 27, 35, and then the third column is going to be salary. I am not specifying any row indexes in here. All right, so these keys in this case are going to become the column names. I have a name column, an age column, and a salary column. And then as values, in the first row, I have name Smith, age 42, salary 58,000. Then in the second row, I'll have name Jones, age 27, value 39,500, and so on. So let's see this. Here's T1. Okay, so I've got columns, name, age, salary. In those columns, the values are, for the first row, Smith 42, 58,000, and so on. And the default labels here are just the integers 0, 1, and 2. Okay, so in fact, if I ask for T1's index, I get told that it's a range index starting from 0 and going up to but not including 3. Okay. Here, I did not bother using the print function. I just typed T1 as the variable name, and my interactive idle shell displayed T1 for me in a nice format. If I say print of T1, in idle, I just get the same thing. Now, if you're using something other than idle, like if you're using Spider or what have you, then the print output may look differently depending on what your integrated development environment is doing. It turns out that if you have a table that has many, many, many columns, or for that matter, many, many, many rows, only the beginning columns and final columns will be displayed, or only the beginning rows and final rows will be displayed, with the ellipsis ... displayed to indicate that there's other columns in there that aren't being shown by default, or other rows in there that aren't being shown by default. You may be able to force the entire data frame to be displayed by setting this pandas option. I'm not going to bother to do that. Okay, so this is one way of creating a data frame. We've set up a dictionary in which the keys are column names, excuse me. The keys are column names, and then we have lists of values for each row in those columns. Notice that it's important that these lists be the same length. By the way, I said that these are lists here, lists of values, but they could just as well be tuples of values rather than lists of values. Here's another example of how to create a dictionary. This time I'm using a list of lists for my values. So my list here, let me copy this thing over, and I'm going to make the format a little easier to look at. Okay, so my list is a list of 3 lists. Each of those lists represents one row of the data frame. Notice that I do not have any column names within the data in this case. I only have the data rows within here. So when I create a data frame using this list of lists for the data, I'm going to need to specify an additional argument, which is the column names. Columns gets, and then in this case I'm using a list of 3 column names. I could just as well have used a tuple of 3 column names. The point is that since each row here has 3 values in it, I want to have a column name for each of the columns. So let me copy that guy over. I'm going to call this T1A rather than T1. We're going to see that the contents of T1A and the structure of T1A is going to be identical to the structure of the T1 that I created by using the dictionary. Okay? All right, so there we are. So the data, the individual cells within the table, have Smith 42, 58,000 as the first row, Jones 27, 39,500 as the second row, and so forth. And I'm specifying the column names separately, whereas in the dictionary, I was able to use the column names as the keys associated with these lists of values. All right, so here's what T1 looked like that I built from my dictionary, and here's what T1A looks like that I built from my list of lists with the addition of column names. Yay, they're the same. Okay. Here's yet another way. So there's all kinds of ways of creating data frames. In this one, I have 3 separate dictionaries giving the basically these are going to be treated as the column name and value for a given row. Okay, so column name has value Smith, column age has value 42, column salary has value 58,000. And I'm setting up that information for 3 rows here that I'm just calling ABC. Then I'm creating a list of those 3 dictionaries. All right, so this is sort of upside down from what we did 3 slides ago. Here we created a dictionary, a single dictionary, in which we gave 3 keys. Those are the column names. And associated with those keys, we had 3 values representing the row values for each of those columns. This time around, we are specifying the column name and the row value for 3 rows, and we're setting up a list of those dictionaries. So we've got a list of dictionaries rather than a dictionary of lists. But we'll get to the same place. So let me copy this stuff in. This is the most verbose way of doing things because I'm having to repeat the column name in each of these dictionaries. And if I make a mistake and don't get the columns names to match, then I'll get yelled at when I try to create my data frame. All right, so here's my 3 dictionaries, and now I'm going to create a list of these dictionaries for my data, A, B, and C. And then finally I can create my data frame. This time I'm going to call it T1B, pd.data frame with D as the argument. All right, I don't have to specify the column names. The column names are contained within the dictionaries that describe each row. So here's T1, here's T1A that I created using a list of lists, and here's T1B that I just created using a list of dictionaries. And they're all the same. So which one is better? Well, none of them is better. They're all equally reasonable. Basically, which one to use depends on the structure of the data that you get from your data source. If if the data source is easy to form into a dictionary of rows, do it that way. If the data source is easy to form into a list of dictionaries, do it that way. If the data is just in a list of lists and you want to create column names yourself, do it that way. But in any case, all 3 of these result in getting for us a data frame of named columns with labeled rows. By the way, if I ask for the type of T1, I do get told that this thing is a pandas data frame. If you want to do experimentation on a data frame, it's a good idea to do your experimentation on a copy, not the original data frame. Because if you mess up your original data frame, there won't be any trivial way of getting it back other than recreating it again from scratch. There is, fortunately, a method, .copy, that you can use to create a copy of a data frame. So the type of tcopy here, which is a copy of T1, is data frame. Tcopy is equal to T1, and the comparison here is done on a cell-by-cell basis in the same way as if we were comparing two ND arrays. But I can test whether tcopy is the same object as T1, and that's not true. All right, so T1 is a completely independent, but at this moment containing the same columns and rows and values as T1. You might think, this turns out not to work. You might think that you should be able to say tcopy, let's say tcopy A gets a new data frame constructed from the existing data frame. This is a little bit shocking because it doesn't actually create a new data frame. If we give a data frame as our argument to the data frame construction function, the data frame construction function realizes, oh, that thing is already a data frame, I don't have to do anything. And in this case, tcopy A is okay, okay. They're not the same for some reason. Oh, I understand what the problem is. This is very subtle. Okay. Here's T1. Here is tcopy A. Here is the ID of T1. Here is the ID of tcopy A. And the ID numbers are not the same. However, each of these columns is represented as an ND array. So I've got an ND array of names, I've got an ND array of ages, I've got an ND array of salaries, and it's those things that are the same. So if I ask for, and I'm jumping ahead slightly here, if I ask for T1 sub name, that is a series which is built on top of an ND array. If I ask for tcopy A sub name, that is also a series built on top of an ND array. If I say T1 sub name to get that column, and then sub 0 to get the sub-0 item, okay, that's Smith. All right, T1 is my entire data frame. T1 sub name is this entire column of the data frame, which is a series. And within that series, item sub 0 is going to be Smith. Now, if I say T1 sub name sub 0 gets Ostlund, value is trying to be set on a copy. Oh, okay. So it did work. I just got a warning that something funny might be going on. And if I look at T copy A, what I'll see is that it also got affected, because even though the data frame T1 and the data frame T copy A are not technically the same, the series that they contain in the columns are the same. So when I modified one of the cells in this series in T1, it had the effect of modifying the same value in that same series, that same column in T copy A. All right, so I'm not going to worry about whether you fully understand all of the details I just described there, but be aware that you cannot use the data frame construction function as a way of fully copying a data frame. All you're really doing is making a copy of sort of the shell of the data frame, that is the column names and the labels, but the data, each individual column is going to be referring to the same individual column in the original data. So don't do it. Bad idea. Okay. Now, let's go back to T1. Oh, I messed up here. So I'm gonna now say T1 sub name. Actually, I've got T1 copy sitting around here, don't I? T copy, which still has Smith in it. So I can be clever now, and I can say T1 gets T copy dot copy. This is why you should never do experiments directly on your original data frame, because you may wreck your original data frame by accident. Now T1 is back to being a copy of T copy, and so it does have Smith as the name value for row sub 0. Just like I did with series, I can rename the index values here by using a dictionary to specify the original value as the key and the replacement value as the value associated with the key. So person 1 is going to be my new key for the first row. Person 2 for the second row. I'm running out of space here, so I'm going to type 2 colon and person 3. Come on, 3. On the next line down, there's the end of my dictionary. Here's the end of my function, and I just realized, fortunately I didn't hit the enter key yet, I need to say in place equals true. Otherwise, I will get back a renamed copy of T1. Okay, so now instead of the default labels 0, 1, and 2, I've got these specific string labels, person 1, person 2, person 3. I showed you that I can access a particular column of an ND array, of a data frame, excuse me. I can access a particular column of a data frame by giving that column name inside the square brackets. To get a row, you may or may not remember this, but I can say .loc with a row label to get a particular row. All right, so whereas T1 sub name gave me the name columns, Smith, Jones, and Zhang, T1.loc of person 1 is going to give me a series constructed from that first row. Okay, so, and notice that the column names are now used as the labels for the items in that series. All right, so name is Smith, age is 42, salary is 58,000. Whoops. That was too far back. I also wanted to point out this alternative. You can use iloc in a data frame just like you can in a series. So T1, all right, so notice the original T1 here. Person 1, I shrank my window. There we go. Person 1, that's the initial row in this data frame. I can think of that as being row sub 0, and I can access row sub 0 by saying T1.iloc. That is integer location sub 0. So that gives me back the same thing as T1.loc of person 1. All right, I'm going to create new T1 as a copy of T1. So new T1 now has these labels: person 1, person 2, person 3. And I'm going to rename these labels this time around from one string to another string using actual persons' names rather than these tedious person 1, person 2, person 3 things. Rename, and my index again is going to be a dictionary mapping from the existing labels to the new labels that I want. So instead of person 1, I'm going to have Bob. And instead of person 2, I'm going to have Mary. And instead of person 3, I'm going to have Jay. Wow, I'm just about out of space there, but I'll get in my curly brace, and then I'll get in my parenthesis to conclude the rename function. I forgot to say in place equals true. So instead of actually directly modifying new T1, it gave me back a modified copy of new T1. Okay, so new T1 has not actually been changed this time. Let me redo this. I'm going to do J on the next line down. Person 3 is J. That's the end of my dictionary, and I'm going to say in place equals true. There we go. Instead of renaming every row, you can selectively just modify certain rows. In this particular example, I'm specifically not doing an in-place change, so I'm not actually modifying T1 itself. Here's T1, which still has person 1, person 2, person 3. And if I say T1.rename with index, and my dictionary only contains a value, one key value pair, then only that key value pair is going to be affected. And because I didn't say in place equals true, it doesn't actually modify T1, it's just showing me a modified copy of T1. T1 itself hasn't been affected. Multiplication of an entire data frame will work fine. On a column-by-column basis, it works as though each column was a series. You just need to be aware here that the behavior of the star operator is going to depend on the type of the column. Now this is a little fishy because okay, so we have a bug here on the slide I just noticed. T1 has columns ordered as name, age, salary. For some reason down here, they got changed to age, name, salary, which is incorrect. And then that incorrectness is carrying through here, age, name, salary. So the example that we're going to see when I do this interactively is going to be similar, except that the name column is going to be first, and then age, and then salary. So if I say T1 times 3, the effect is to multiply each column by 3. For a string, that means repetition. So I'm going to get Smith, 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 Jones, 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 Zhang, Zhang, Zhang. Then I'm going to get 3 times 42, 3 times 27, 3 times 35 as the ages. And then 3 times these salaries as the salaries. All right, so those are correct. They may just be a bit surprising because of the string repetition. Similarly, you can add together 2 data frames as long as the data frames have identical column names and identical row labels. T1 plus T1 well, is effectively the same as multiplying T1 by 2. So I get Smith Smith for the strings, and then 84 and 116,000 as far as the age and the salary. These are very small data frames. It's much more common for a data frame to have, hundreds of rows and, let's say a minimum of half a dozen columns or, maybe a few dozen columns. It's possible for these data frames to become enormously large. And so in order to just see the first few rows of a really large data frame, you can use table in our case would be T1, and then use the head method. By default, table.head gives you 5 rows, or up to 5 rows. In T1, there's actually only 3, so I'm going to see the entirety of T1. But if I say T1.head 2, I only get the top 2 rows. Tail is the opposite of head. And so if I say T1.tail 2, that gives me the last 2 rows. So what good is that? Well, again, imagine that we've got a data frame showing us for each day of the year, where the dates of the year, the dates of the days of the year are the row labels, and the column names are counties, and the cell values are new flu cases. If I just wanted to see recent history, I would use tail for that. Show me the last 10 days worth of the flu information. Or if I wanted to see the beginning of the year, I would say head. Okay? Now, within T1, there are basically 3 components. T1.data. Whoops. There we go, sorry. T1.values is an ND array of all of the values contained within the data frame. T1.columns is the column names represented as a so-called index. And then likewise, T1.index, that's the row indexes. Okay? You can invoke a toList method to convert that into a list rather than an index or an ND array. So T1.columns is an index. T1.columns.values is just the values as an ND array, and T1.columns.values, and we already know that toList will convert an ND array into an ordinary list. And then we can do the same thing for the index labels. All right, so now let's take a look at how to access columns, sets of columns, rows, sets of rows. In T1, I have 3 columns, name, age, and salary. One way of accessing a particular column, as I've shown you, is to use the column name as the subscript. So if I say T1 sub age, I get out just the age column with the as a series. Okay, this thing is a series, and the labels of the series are the same as the row label. The index labels for the series are the same as the row labels for the data frame. All right. Since age does not contain any spaces or arithmetic kinds of symbols, as a shortcut, I'm allowed to say T1.age. And that gives me exactly the same result as saying T1 sub age. I personally don't like to use, I tend not to use the shorthand for the simple reason that often column names do have things like spaces in them, or like a % sign in it. Let's suppose that you were dealing with financial data, and one of the columns here was the return percentage on a stock. Well, then your column name might be return space with a % sign, and that % sign is going to be treated as a modulus operator if you just try to access the dot return space %. The % now is all of a sudden a modulus operator, and that's going to fail. Okay, so T1 sub age got me one column. T1 sub salary will get me a different column. I can do this so-called fancy indexing. Here on the slide it's called a slice notation, but actually a slice notation means to use a colon. So this is actually technically a fancy index. Let me remind myself what T1 contains. If I say T1 sub, and then my fancy index, I can give a list of column names in the order that I want to see them. Okay, so this fancy index is going to generate for me a data frame with person 1, person 2, person 3 as the row labels, but the columns are going to be ordered with salary first, then name, then age. Okay, so this is a simple way of reordering your columns. Here we're just showing doing addition. I'm not going to bother with that. All right, so T1 square brackets and either an individual column name or some kind of list or set of column names, tuple of column names, will give you just that one column or those few columns in the order that you want. In the row direction, you can't use just a plain row label or just a plain row number. Both of those give me errors. What I have to use to access rows, and it takes a little while to get comfortable with this, you have to say t1.loc and then give your row label. So t1.loc subperson1 is that particular row, or t1.iloc sub 0 if I want to use the equivalent integer subscript. Okay? Name, age, salary. Now, when I use either loc or iloc, I can get a particular cell by using the notation row comma column. So if I say t1.loc and then I give my row label person2, then I can give a column name, to access that particular cell value. Okay, so t1.loc, row comma column. Just like accessing a particular item in an array in mathematics. You specify the row and then the column with a comma in between. And so that gets me back that particular cell. Now, I've shown you that for the row, I've shown you that for the column, you can use a fancy index rather than an individual index. For the rows, you can also use fancy indexes, or you can use slices. So let's see what's happening here. So here's T1. Let me say T1.loc, and now let me use a slice going from person 1 up to person 2. And let me ask for the salary column. Here I have a slice of rows and one column. Now, previously when we've done slices, we've used integer values to specify the beginning item and one past the ending item in a slice. Somewhat strangely, if your concluding item in a slice, if you're dealing with slices on strings, then the meaning is from this first string up to and including that last string. So the meaning of the second item in the slice changes from up to but not including to up to and including. All right, so I got person 1 up to and including person 2, but just the salary values. On the other hand, if I use t1.iloc and I say 0:1 with the salary column, now I get from row sub 0 up to but not including row sub 1 and just the salary. So this time I'm only going to get that first row because I'm going up to but not including the second row. What did I do wrong? What did I do wrong? T1 sub. Oh, T1 dot I loc sub 0:1. T1 dot I loc 0:1 salary. Yeah, I forgot. If I use iloc, all right. If I use iloc to use integers for the rows, it turns out I also have to use integers for the columns as well. So that was my forgetfulness. So here's T1. I said T1 dot loc sub from person 1 up to and including person 2, and I just want the salary column. So that worked fine. Now, the mistake I made was when I say T1.iloc 0:1, I also have to specify the integer corresponding to the salary column. That's going to be the integer 2. There we go. So I got from row sub 0 up to but not including row sub 1. So in other words, just row sub 0. And column 2, which is the salary column. Okay. All right. So I've specified an individual row and a column. I've specified a slice of rows. And a column. Now, let me specify a fancy index on rows. Person, I need another square bracket. Person 2, person 1, and a column. So in each of these three cases, I'm only asking for one column, namely the salary column. Here I'm getting the cell value at row person 1, column salary. Here I'm getting the series from person 1 up to and including person 2 from the salary column. Here I'm getting person 2 followed by person 1, and I'm getting the salary column from each of those two rows. Okay, so notice that I swapped the ordering of person 1 and person 2 here by using the fancy index. We can do the same thing with integer subscripts if we use iloc. T1.iloc 0, 2. T1.iloc 0:2, 2. T1.iloc square brackets 1, 0, 2. Okay, so this gave me from row 0 up to but not including row 2, so that was person 1 and person 2, and the salary column. Here I'm going to get person 2 followed by person 1 and the salary column. All right. Individual subscripts, slices of subscripts, fancy indexes of subscripts. We've done that for the rows. Now we can do the same thing for the columns. Okay, let me, these are kind of duplicated examples here. Loc and iloc. This is row column. If I give column row, that's an error. Okay, T1. I believe this is just going to be an error. I think this one here, where I give a row number and a column. Oh, that is going to work because they have modified T1 here to have integer row labels. So T1 dot loc sub 1 comma age. For me, that's not going to work because there is no row whose label is 1. But if I change the rows in here from person 1, person 2, person 3 to 0, 1, and 2, then that would have worked. All right, so let's take a look at columns. I'm just going to continue doing my own examples here with T1. So T1 dot loc followed by a row. Let me do person 2. Okay. So the notation goes row comma column. And I've shown that we can give an individual column salary. That's not right. Salary. All right, so that gets me an individual cell. I can say T1.loc with a row label, and now I can give a actually, I don't remember whether this works. Yeah, cool. Okay. I guess I just haven't done that for a while. So yes, you can ask for a slice of columns. And you can, actually, I mean, a slice of columns is kind of an uncommon thing, unless the columns happen to be like alphabetically organized or something like that. It's more common to use fancy indexes to select certain rows from just a subset of columns. Let me get the name first, and then the salary next. And maybe I just don't want the age at all. Okay, so for the row person 2, I've got the name first and the salary next. All right, so individual columns, slices of columns, fancy indexes on columns. Just like we did individual rows, slices on rows, fancy indexes on rows. And I can combine all of this crazy stuff together. So here's T1. Let's suppose that I just want Smith Smith in the last column. I'm sorry. Let me move the name column to the end and the salary column to the beginning. And let me move person 1 last and person 3 first. I can do all of that by saying T1.loc, all right, because I'm going to use names for rows here. My fancy index is going to be give me the row person 3 first and the row person 1 second. And in those rows, give me the column salary first and the column name second. All right. So notice that I have selected just 2 rows, and I've changed the order of those rows. I've got person 3 followed by person 1. And I've also selected 2 columns and changed the order of those columns. So I've got salary as the first column and name as the second column. And I can do all of this stuff using iloc with numerical indexes. So I want, let's see, row sub 2 followed by row sub 0. And then column sub 2 followed by column sub 0. Same thing. Okay. All right, so I think that covers all of this mess of accessing. We can now access entire rows, entire columns. We can access individual cells. We can access subsets of rows, subsets of columns, using either slices or fancy indexing. And we can access rows and columns either using strings, if the labels are strings, or using integer subscripts by using .iloc. Now, a side effect is an unwanted modification to some information. For example, if you have an object A sitting around and you say B gets A, that is not creating a copy of the object A. It simply sets up B as a reference to the same thing as A. And the bad news here is that if you modify B, you will end up changing A as well. So we've already talked about the copy method that the data frame data type provides. If you say B gets A.copy, then B will be a completely independent copy of A. And you can modify B without worrying that it's going to affect A. I created here a data frame called Y from a few slides ago. I realized that I need it for this upcoming stuff. This was created back on the slide here. It happens to be slide 21. And so I copied and pasted that data frame creation statement. And so here is what my Y data frame looks like now. It has Bob, Mary, and Irene as the row labels, name, age, and salary as the column headers, and then data for those rows and columns. T1, in these upcoming examples, I'm going to want to have integer indexes for T1 rather than these person 1, person 2, person 3 string indexes. Fortunately for me, I have T1 copy, or I think it's called tcopy, sitting around, which does have the original integer indexes. So I'm going to create T1. I'm going to recreate T1 as a copy of tcopy. All right, so now I've got the T1 data frame that I need for these examples coming in this set of slides, and I've also got the Y data frame that I need. You'll notice that these contain the same data, but in the case of T1, I have integer row labels. In the case of Y, I have string row labels. Okay, if I say X gets T1.copy, then X is a completely independent copy of T1. It looks the same at this point. If I say Z gets X, whoops, Z gets X, not Z gets Z, If I say z gets x, this introduces the problem of side effects, because z now is really just an alternate name for x. And if I say z sub age, that is a column of z. And if I say z sub age, and then I access the row, the integer row at slot 0, and assign a value of 100 there. Okay, so z sub age is this series taken from the age column of z, and if I say z sub age dot iloc 0 gets 100. Okay, this is a warning on a copy of a slice. Z does get affected, but unfortunately, so also does X, because X is actually just the same data frame. Z is just an alternate reference to that data frame X. Okay, so that's just a bit of a long-winded reminder / warning to not just say variable gets variable and assume that your new variable is a copy of the original one, because it's not. It's simply an alternate reference. Now, how can we change information contained within, in this case, a column? Well, x sub, I want to go back to T1. T1 sub age is my column of ages. I can modify T1 sub age to new values. I simply give some iterable that has the same number of values that there are rows in the data frame. Here I'm saying 50, 65, and 22. These are going to be my new ages. And poof, it works fine. And I have now modified all of the ages in the age column. To add a brand new column, oh, that was some pretty ugly highlighting. I can give a new column name as a subscript of my data frame. This is very much like giving a new key name to create a new key value pair in a dictionary. So here I'm going to say y, here's y, and I'm going to say y sub hired. Well, there is no hired column currently, so this is going to end up creating that column. And I've got 3 rows, so I'm going to type in 3 years of hiring here, 2018. And poof, that added that hired column to the Y data frame. I need to also do the same thing for T1 for upcoming examples. T1 does not have that hired column. I want to add that hired column to T1. Okay. In terms of adding a row, you can do the same kind of thing, but you use .loc or .iloc to indicate the new row label that you want to have. So Y currently does not have a row labeled Fred. I can say y.loc Fred to create such a row. Well, if I just leave it at that, I'm trying to access the row, and of course the row doesn't exist. I get all kinds of yelled at. But if I say y.loc sub Fred gets, now I need to be careful to give data that's of the same data type as what exists in the columns. So first I have the name, which is going to be Barnes here. Then I have the age, which we'll say is 38. Salary, which is a float, 42,750.0, and hired year is an int, 2019. And poof, I have now changed. I have now added a row to Y. Now, for T1, which is using integer indexes, if I try to say T1 dot loc of 3, again, I get yelled at. So for T1, I'm instead going to use an append function, which I could have used for Y as well. I'm going to say T1 dot append, and now I specify a dictionary containing the column names as keys and the values as values associated with those keys. So my first column name is name, and the value associated with name in this appended row is going to be gray. Then I have age, and the age of this person is going to be 50. Then salary is going to be 33,250. And I've run out of space, so I'm going to hit the Enter key. And my final column is hired, 2017. All right, so that's the conclusion of the dictionary representing the values for this row that I'm appending. And weirdly, I don't have an in-place argument for T1.append. What I have instead is this ignore index thing. I'm also getting this warning here saying that dataframe.append is deprecated. A lot of things are deprecated and tend to hang around for a while, but I guess we could use concat for concatenate instead of append. That's all right. Now, I want to point out that T1 was not actually changed here, which is kind of strange. Despite me using the ignore index equals true. So what I'm going to have to do is to reset T1, the variable T1, to refer to the modified copy of T1. All right, so I will execute the same append again. But I'm going to say T1 gets the result of doing all of this stuff. And now T1 has been modified to contain that new row. Now, when you use iloc, okay, here's why. When you use iloc and try to add a row, rather than me manually typing this in, I'm going to cheat and copy and paste here. Okay, so let me copy and paste. Okay, I get yelled at because for whatever reason, iloc is not allowed to use an index that doesn't already exist. So the indexes that I have currently in Y, the integer indexes that correspond to the four string indexes here are 0, 1, 2, and 3. So 0 for Bob, 3 for Fred. And if I try to use iloc sub 4, for whatever reason, Pandas doesn't like that and won't allow that to work. Okay. All right, so we've taken a look now at how to add a column and how to add a row, and we've warned you about a couple things that don't quite work. If you want to get rid of a row or a column, you can use the drop method. So here I have y, and if I want to eliminate the row that has the label Irene, I can say y.drop and then give that okay, notice that this is taking labels, not just one label. So I'm giving a list that just contains Irene. And there we go. Now, as we've seen before, by default, this doesn't actually modify y. Irene is still there. So in this case, I do have the in-place argument that I can use, in place equals true, and that will directly drop Irene from y, so that when I display y again, I'll see that Irene is now actually gone. So that's for rows. You can also drop columns. In a data frame, all right, here's T1, which still has 4 rows in it. Let's suppose that I want to drop this column hired. In a data frame, the first, or the primary dimension of the data frame here is the row dimension. That's what's called axis 0. If we're thinking in terms of the XYZ axes in a three-dimensional image. In Python, those are considered to be axes 0, 1, and 2 rather than X, Y, and Z. So the 0 axis is the rows. The 1 axis is the columns. If I want, let me look at y again, as an alternative to saying y.drop Smith, I could say y.drop axis equals 0. You'll notice my help message went away. Okay, I think you can see this on the video. Axis is 0 by default. And so if I say drop Bob, axis equals 0, that means to drop Bob as a row. Although, of course, it didn't actually go away. If I say y.drop and I give hired with axis equal to 1, axis 1 is the columns, and so this is how I can get rid of a column. Although, again, I'm not changing y with either of these examples. Here on the slide, we're modifying T1. If I say T1.drop, if you want to just drop one thing, you can just give its name. You don't need to give a list. Okay, I have dropped the hired column. And if I want that to be in place, then I just say so. Okay, and so, whoops, what happened there? Oh, I just typed an extra parenthesis by mistake. There we go. So now I have permanently dropped the hired column from T1. You can transpose a data frame just as you can transpose an ND array. T1 dot capital T is going to take all of the column names and make those rows, and all the row labels and make those columns, and just flip the values around the diagonal axis. You can also sort rows and or columns. All right, so here's T1. Notice that for columns, I have name, age, salary. Maybe I would prefer to have age, name, salary. Also for, well, the rows are labeled 0, 1, 2, 3, which is sorted. But, okay, so if I say T1.sortIndex, that's not going to change anything because the index is already sorted. If I say T1.sortIndex, ascending equals false. This is kind of humorous to me. You would think if you wanted things sorted in descending order, you ought to be able to say descending equals true. But no. Ascending is what you get by default. So if you want descending, you have to say ascending equals false. And so now we have the rows sorted in reverse in descending index order. I can also do this in place if I wish. Just doing a plain old sort index doesn't actually modify anything. If I do this in place, then it will. All right, so I'm going to say in place equals true. And now T1 has the rows reordered. As we talked about with dropping columns, you can do a sort index on axis 1. And that will reorder the columns instead of reordering the rows. So if I say T1 dot sort index axis equals 1. Now I'm going to sort the columns in ascending order. So I get age, name, salary. But in the example here, we're going to ask for them in descending order. So let me just do that. T1 dot sort index axis equals 1. Ascending equals false, and now I've got salary, name, age. Again, this did not change T1 because I did not say in place, but I could use in place equals true. If you want to sort on a particular column, instead of saying sort index, which allows you to sort the row labels or the column names, you can sort on the values contained within a column. All right, so here's T1, and I can say T1.sort values by, and then give the column that I want to sort on. So now I'm going to get what? Gray, Jones, Smith, Zhang. Gray, Jones, Smith, Zhang is my sort order. And again, I could do that in place if I wanted to make that a permanent change. There are a variety of functions available for doing statistical operations on the data within your data frame. You can ask for sums of values in columns, means, variances, standard deviations, medians, on and on. I'm not gonna read all of these to you. Here's a here's a pointer to some documentation that will describe all of the statistical functions available. Let me do a few demos. T1 has name, age, salary in it. Actually, it looks like these examples are using sorted columns. So let me say T1 dot sort index axis equals 1 in place equals true to put those in sorted order. Now T1 dot sum will compute for me a series in which the column names are going to be the labels, and the sums of the columns are going to be the values. Now, a sum of integers makes sense. A sum of floats makes sense. Actually, weirdly, a sum of strings also makes sense, but what we're going to get is Gray, Zhang, Jones, Smith, all as a long string. So, not sure how useful that is, but that's what happens. I can, instead of sorting the whole, or instead of summing the whole data frame, I can just select a particular column. So there's the sum of the ages, and I could do likewise to compute the sum of the salaries. If I want to know the average age or the average salary, I can compute the mean. Here, mean doesn't make any sense for strings, and I get yelled at. Well, this is a warning, not an error. I get told dropping of nuisance columns because the mean of a string doesn't make any sense. And so what I get out here is just the age and the salary. I could have added this additional parameter, numeric only equals. Okay, so I guess that's deprecated. Dropping. Okay, so they're saying select only valid columns. So I could do that. I could say T1 sub and then use a fancy index, age, salary, to just get those two columns, and then on those I could ask for the mean. And that will prevent me from getting yelled at about the string column. Now, notice that what's getting returned here is a series. Okay, so this thing here is returning a series, and we know how to access a particular item within a series. We just use square brackets with the, or I guess in this case we could say .loc, and then the particular item from the series that we want. So there is the from the series that contains the means of the ages and the salaries. I can ask for just the age, and I get this particular value. And I can then use that in a print statement with a format code to display that in some formatted way. What's being done in this particular example here, instead of computing the means of two columns, here we're just computing the mean of one column, which does give me back just a single value, which I can then pass in and format. Here's the describe function. This gives what are called descriptive statistics, but only of the numerical columns by default. So I'm getting the number of records, the mean of the values, standard deviation, and then minimum, maximum, and these quintiles, the 25th percent, 50th percent, and 75th percent quintiles. Okay, and this again, this is a data frame, T1 dot describe is a data frame, So that means that I can say t1.describe, and I can access a particular row. So I can access the mean, .loc of mean, and I get the means of the age and the salary as a series. Okay. ID min and ID max return for me the indexes of the minimum and maximum values. You can also read a variety of different kinds of file formats into a data frame. You can read from a comma-separated value file, in which the assumption is that the first row contains the column names, and subsequent rows contain data. Likewise, we can read an Excel spreadsheet in native form. We can read an HTML document, a JSON document. If we have a data frame pickled in a file, we can read that pickled data back again. And likewise, we can write data to various different formats of files. Here, okay. Let me create the scores file. I'm going to pause for a moment so that I can do that. Okay, so I have used Notepad to create this file, scores.csv. The pound sign, sharp sign at the top here is going to be treated as a comment. And in here I have these column names, date, team 1, team 2, score. And then I have data rows with dates, team 1, team 2, and score for some football games. Now, this file does not have any index column. So the index labels for this data are just going to be, by default, 0, 1, and 2. All right, so that file now exists, and let me read it in. Scores gets, I'm going to build a PD data frame by reading a CSV file. Scores.csv. Okay, and I don't need to worry about doing any opening, any looping, any closing. It just... Why didn't it work? I have a nasty feeling that I created it in the wrong directory. So let me try that again. Let me revise, or let me retry my read CSV, but now let me put in the actual location on my machine. So it's c:\users jostland downloads. Okay. Alrighty. What the heck happened there? There we go. Okay, users Jostland downloads scores.csv, and yay, that time it worked. And, whoops. Oh, it did read in that first line. Okay, so that's a mistake. Let me pull back my file here and get rid of that line. We're going to save that and do it one more time. There we go. Okay. And so we can see here that I did get the data frame pulled in from the CSV file. Now, I can make modifications to the data. I mean, it's a data frame. We can make modifications to the data, so I'm not going to. Well, I guess I should. iLoc2. Now, we're in Pittsburgh, and as Pittsburghese, it is a requirement of living in Pittsburgh that you hate the Cleveland Browns. So what we're doing here is we're saying scores.iloc2 and then team2. Okay, so scores.iloc2 is the row, the sub2 row. And within that row, which is at this point going to be represented to us as a series, within that, one of the pieces of information is labeled team2, and we are going to say that that should be poopy heads. We are masquerading as third graders here. All right, so we have now got Team 2 as the poopy heads. And if we use the toCSV function, that will create a CSV file from this data frame. So I'm going to say scores.toCSV. Now I want to store my revised file in the same directory where the original file is located. So on my system, I'm going to say c:\users jostlund downloads new scores.csv. And I don't want to store my index labels into the file, just like my original file did not have labels in the file. Poof, it happened. And if I now use Notepad, I can find, let me pull up Notepad here. Okay, so now I can open that new file, or that, whoops, sorry. You can't see what I'm doing here. So, well, I'm just going to say new files or new scores.csv. And there it is. Okay, so I have now successfully stored the modified name for my team into my file. And if I do another read CSV to pull that back in, I'll get the same data frame that I had. This time with the appropriate renaming of Team 2. Now, if you don't use the index equals false argument when you use toCSV, if you just write the output to a file, then the first column will be the row indexes. So let's do that. I'm going to do this same thing again, but instead of new scores, we're going to call it other.csv. And when I now open that file with Notepad, all right, let me open others.csv, other.csv. You'll see that it has added a column with the row labels. Now, to read that back in, I'm going to skip this page that shows what goes wrong. When we used read_CSV, read_CSV assumed that there were not row labels stored in the file, and it created default values 0, 1, and 2 for the row labels. But now that there are row labels stored in the file itself, if I do that with read_CSV, read_CSV assumes that these values here, 0, 1, and 2, are data instead of labels. And I get these default labels 0, 1, and 2 for all the stuff in that file. What I need to do is to add another option or another argument. I'm going to say y gets pd.read CSV. I'll give my file name. And I'm going to say index column is column sub 0 in the file. So now y is identical to scores. All right. I'm going to let me decrease my here's my 2 notepads. I'll just get rid of those. I want you to see the deranged volume of options available in read CSV. When I say pd.read CSV, now a lot of this stuff is off the right side of my screen here, but you can see that the read CSV method has got about 50 different options for specifying details about how to read in a comma-separated value file. There's no way you can remember all this stuff. You basically just have to look it up in the documentation and pick out which options are required for what you're trying to do. So in our case here, the first file name, the first argument was the file name. And we had to specify, in this example, index col equals 0 to persuade read CSV that there were already index labels in the file itself, and so it should pull in and use that index column. We said index col equals 0. All right, well, that is a vast amount about pandas. We've taken a look at how to create data frames from scratch. We've taken a look at how to read in data frames from files and how to write data frames out to files. We've talked about how to create and remove columns, create and remove rows, reorganize and subselect columns, reorganize rows, how to add, I guess I said that already, add new columns, add new rows, and also a variety of statistical capabilities that Pandas provides for analyzing the contents of a data frame. Okay, all right, take care, bye.